We will continue with melting and crystallization of lipids. Melting and crystallization of lipids play an important role in determining final quality attributes of food products. Because the production of food products with desirable properties depends on an understanding of the major factors that affect the crystallization and melting behavior of lipids in foods. This figure here is a simple but useful illustration of melting and crystallization. Melting is converting a solid fat into a liquid form, whereas crystallization is the opposite. It's converting a liquid oil into a solid form. So when do lipids change from a solid to a liquid state? When its temperature is raised above the melting point. So what external factor is needed for this phase change? It's simple, it's heat. For melting, we need to heat the fat. But what kind of heat we are talking about? It's the latent heat of fusion. So latent heat of fusion applied in melting. So what is the definition? So it's the heat that has to be applied to the solid fat to increase internal energy to the point where all molecules vibrate, leading to disintegration of this solid structure. So these are the individual 3-acylglycerol molecules here. Looks like a fork. They can be this way or they can look like this. 3-acylglycerol. So as you see here, individual 3-acylglycerol molecules. So these 3-acylglycerols organize in a way depending on the physical state of the lipid. Here in solid state, they pack more efficiently. Solid fat is more organized. It's a well-ordered structure compared to liquid oil, as you see here. The strength of the bonds between the lipid molecules is greater in the solid state than in the liquid state because the molecules are able to pack more efficiently. So 3-acylglycerol molecules, 3-acylglycerols pack more efficiently. So during melting stage, entropy of the system increases, meaning the system becomes more random, disorganized as seen in the liquid oil. The tag molecules, 3-acylglycerol molecules, are randomly distributed and less organized. So what is entropy? Entropy tells us about the organization of the system. So we said during melting, entropy increases. System becomes more disorganized. And this transition in melting is endothermic. It's endothermic because energy, heat must be applied to the system to pull the molecules further apart. Melting results in the 3-acylglycerol molecules within the lipids becoming less organized. So for crystallization, we need to cool a liquid oil. So it's the opposite. We are cooling the oil to form crystalline structures, a crystal network. So here we are talking about cooling the system. When cooled, the 3-acylglycerol molecules form an organized structure and become solid. It results in the 3-acylglycerol molecules within the lipids becoming more ordered. It's a well-ordered structure. It is solidified. So what happens to entropy? So in this case, entropy decreases. Entropy of the system decreases. And this transition is exothermic. It's liquid to solid transition. It's exothermic because energy is released as the molecules come closer together. So these are the two important behaviors of lipids in foods. So they affect the textural and sensorial properties. They affect the taste. The crystallization of lipids is more complex compared to melting. It involves a number of stages like supercooling, nucleation, crystal growth, and some post-crystallization events we will see later in the other slides. Okay, let's continue. Now we are able to visualize the packing of 3-acylglycerols in lipids. And packing is very important and it affects all physical properties of the lipids. Let's see the melting point. If lipid is composed of pure 3-acylglycerols, only one 3-acylglycerol, then we talk about a melting point. But generally, edible lipids melt over a temperature range because they are composed of mixture of 3-acylglycerol molecules. And each 3-acylglycerol in lipid has different melting point. That's why we talk about melting range or melting profile when it comes to edible lipids. Okay, let's write each 3-acylglycerol molecule has different melting points in lipids. And this melting point or melting profile depend on packing of 3-acylglycerols within fat crystals. If packing is efficient, then the melting point will be higher because it will be hard to melt that efficiently packed lipid molecules. It will be a strong structure. Therefore, the melting points of lipids will be higher if lipid contains 3-acylglycerols with longer chain length. Longer chain length. We are talking about hydrocarbon chain. So what do we mean by that? So let's give an example. We might have 16 carbon, a saturated fat as an example, and 18 carbon. So if we have a longer carbon chain, that means we will have higher melting points. And the second one. The melting point of lipids will be higher if lipid contains 3-acylglycerols with straight chain fatty acids. So what is that? Straight chain fatty acids. That means saturated fatty acids. Okay, I'm going to write here. So saturated fatty acids are straight. On the other hand, unsaturated fatty acids are branched. They are bent. So whenever we have unsaturated fatty acids, that means we have a double bond, right? And this double bond, when we have this double bond, it will cause the structure to bend. Because of this bending, we also call them branched fatty acids. So how this affects the packing? Okay. So if we have a straight, maybe you can visualize like this. If we have a straight structure, straight fatty acids, we have lots of straight fatty acids here. That's the first case. And in the other case, we have branched fatty acids. This is just a representation, branched. So in which case we will have a better packing, more stronger structure. The first one, right? Here the packing is better. See, it's well ordered, more organized structure. But in the second case, we have a loose structure. Packing is not good, not very efficient. That's why the melting point will be lower compared to this one. So if our triacylglycerol is composed of straight saturated fatty acids, then the melting point will be higher because of that efficient packing, because of that strong structure. And the last one. If we have more trans fatty acids in our triacylglycerol, then we will have higher melting point compared to cis trans fatty acids. Remember trans versus cis. We have trans and cis. Cis is the natural configuration. So for example, margarine has higher melting point compared to butter. Because in margarine we have trans fatty acids and butter is natural. We have cis configuration. Let's continue. This table shows the melting point and latent heat of fusion of the individual triacylglycerols. If melting point is high, that means we need to apply more heat to disintegrate the structure. So latent heat of fusion will also be high. The fatty acids in a triacylglycerol molecule can all be the same or different. As you see in the table, it can be just composed of 3 stearic acids or 1 stearic acid and 2 oleic acids. The melting points of a triacylglycerol tend to increase with increasing chain length and with increasing saturation. Let's look at the table. The first triacylglycerol in the table is composed of 3 lauric acids. And here we see that lauric acid has 12 carbons. And the other one is composed of 3 palmitic acid. And palmitic acid has 16 carbons. And we said that melting point increase with increasing chain length. So as you see here, 3 palmitic acid triglycerol has higher melting point compared to that one. Latent heat of fusion is also high. And that one has the highest melting point in the table. This triacylglycerol composed of 3 stearic acids with 16 carbons. The melting point is 73 degrees Celsius. And that one has the lowest melting point, 5 degrees Celsius. It's composed of 3 oleic acids. See, actually, the chain length is bigger than stearic acid, but oleic acid is unsaturated. Even presence of one double bond decreases the melting point. And it decreases dramatically. There's a big difference between these two. The chain length is important, but saturation is the major factor affecting the melting point. Let's compare these two. There is 1 oleic acid and 2 oleic acid. And the 2 oleic acid triacylglycerol has lower melting points. Again, the melting points at triacylglycerol tend to increase with increasing chain length and with increasing saturation. But saturation plays the major role in melting point. Okay, let's move on. Solid fat content. Solid fat content gives information about the physical state of the lipids in a food product. It can be expressed as a fraction, so it's a number. It can be between 0 to 1 or as percentage. Between 0 to 100%. So one more 0. For example, in this graph, it's expressed as percentage. It's 100% and 0%. So in this graph, you see a solid fat content of a lipid at a particular temperature. The temperature dependence of the solid fat content is one of the most important criteria influencing the selection of lipids for particular food applications. For example, it's important that margarines are hard enough to retain their shape when stored in a refrigerator or brought to room temperature, but they are soft enough to be spread with a knife. So in this graph, you see a profile of a pure triacylglycerol. For example, it can be just composed of 3 stearic acid. Or maybe just stearic acid, 1 oleic acid, and 1 more stearic acid maybe. And the other one is the profile of edible fat. And edible fats are mixtures of triacylglycerols. That's why they have a broad melting range. So in this edible fat, you will have 3 stearic acid, SOS, maybe palmitic oleic stearic, palmitic oleic, and many forms is possible. But here in this pure one, only this one or this one. It is not a mixture, only one triglyceride. So we have 2 axes. Y-axis is solid fat content and x-axis is temperature. Let's say this temperature is 70 degrees Celsius and this one is 50. Maybe this one is 20. Let's look at the profiles. For edible fat, what is the solid fat content at 70 degree, it's 0. So when we go to 50 degrees Celsius, the solid fat content is like about 40%. So what does that mean? That means around 40% of that lipid is solid at this temperature, at 50 degrees Celsius. So at 20 degrees Celsius, around 80% of that lipid is solid at this temperature. So edible fats has a broad melting range. The physical state is changing in a broad range because it's a mixture of different triglycerides with different melting points. So when we look at the pure one, we just see that we have 0 solid fat content at 50 degrees Celsius. That means it's all liquid. And then when we go to, let's say this is 30, when we go to 30 degrees Celsius, it's 100% solid. 20 degrees Celsius, again 100%. 10, it's again 100% solid at those temperatures. So it's sharp, it's a very narrow range because we only have one triglyceride, only one type. So this graph is important. The solid to liquid ratio at a certain temperature is important for particular food applications. It strongly influences the efficiency of the production process and the final properties of many fatty foods. Okay, let's continue. Crystallization. Crystallization is the other important parameter for lipids. The overall physiochemical and sensory properties of products such as butter, margarine, ice cream, and baked goods are strongly influenced by the crystallization behavior of the lipids that they contain. And crystallization process is more complex compared to melting. It involves several stages. Here, this figure shows the illustration of crystallization process. So in the first stage, the liquid oil is cooled below its melting point. The temperature is below the melting point, but the oil is still liquid. It's called supercooling. The first stage. The liquid oil is cooled below its melting point, or we can call it freezing point. You know, melting point is equal to freezing point because they both describe the same transition of matter between solid and liquid. So the other step after supercooling is called nucleation. Nucleation is very critical in crystallization process. During nucleation, small crystals are formed. I think they are visible. They are like little dots. Very small crystals. So they are called nuclei. It's plural form. Or nucleus. A single crystal. During nucleation, two scenarios are possible. First, the nuclei may grow into bigger crystals, as seen in the crystallization stage. It can go that direction. Or they may melt back into the bulk oil. It might go that direction. So this depends on the size of the nuclei. There's a critical nucleus size. When they are at the critical size, they can overcome the activation energy needed to grow into bigger crystals. Okay, let's write here. By the way, this is R is missing. So at the critical nucleus size, they overcome the activation energy. Okay, it's not raining. And then grow into bigger crystals. This is ants. After crystallization stage, the crystals grow bigger and bigger in ripening stage. They go to ripening stage and then agglomerate and form bigger crystals, crystal agglomerates here. Then even we can separate them, we can filter them if it's needed for a particular food process. So during this cooling, depending on the temperature, some triacylglycerols will be solid, some will be still liquid. Once enough time is given to reach the temperature below the freezing or melting point of all three acylglycerols available in the lipid will be completely solidified with a well-ordered crystal network. So here, the nucleation is the most critical step. So I'm just repeating, there was an interruption, I guess. So nucleation is the most critical step of the crystallization. Let's learn about the nucleation types. There are different types. There are two types of nucleation, homogeneous and heterogeneous. Two types. Here you see true melt. It means the temperature is above the melting point of the lipids. So it's in a liquid state. See, the three acylglycerol molecules are randomly distributed. It's not well ordered. Then you start cooling. Crystals are forming in nucleation step. And at the end, you have a solid crystal lattice. A crystal network in both cases. But what is the difference? So the difference between the homogeneous and heterogeneous nucleation is that in homogeneous nucleation, there is no surface for the three acylglycerols to crystallize on. That's right here. Triacylglycerols However, for heterogeneous nucleation, the crystallization starts on a surface. So that's the main difference. See, that is the surface. Crystals are started to form on that surface. So what do we mean by surface? This surface can be container of the lipid, and maybe a crack in the container, or a dust particle, or a piece of food. Just a surface to initiate the crystallization. In homogeneous nucleation, since there is no surface, tag molecules, triacylglycerol molecules, have to come together. Then crystallization will start. They will form that crystal lattice. So how this affect the energy needed for crystallization? So we need much lower temperatures for homogeneous nucleation because there is no surface. There is an activation energy to form a new surface. Therefore, we need to provide more cooling to form a surface. More cooling. So in heterogeneous nucleation, the surface is already available, therefore it's much easier for triacylglycerols to start crystallization. In real life, almost all crystallizations are heterogeneous nucleation. Because oils are cooled in containers, there are a lot of irregular surfaces such as cracks in the containers. There are also some dust particles entering from air into the containers. These particles also serve as a surface to start crystallization. Let's investigate the triacylglycerol packing structure. During crystallization, tags can pack in different forms. The molecular packing can vary by angle of tilt or chain packing. Occurrence of different crystal forms for a same compound is called polymorphism. Here we are seeing different polymorphic crystals, polymorphic forms. These are the same molecule. It can pack this way or this way. Even length can change. This, like this. Yet the chemical structure is the same, but their crystalline structure is different. The lattice is different. So these are the possible ways of packing for triacylglycerol molecules. So in polymorphism, the most critical thing is the packing of the triacylglycerols. Most common polymorphic forms are alpha, beta prime, and beta. These names come from their shapes. So these black balls are the carbon atoms, carbons. In the alpha form, the triacylglycerol chains are packed in the hexagonal shape. The chains are rotating. The line around the carbon atoms show that they are rotating. Due to this rotation, the chains cannot pack well, and therefore the distance between the chains is big. The distance is big. Therefore, alpha is the least stable form. due to rotation. In beta prime, the chains are not rotating, and chains are packed better than alpha. It's packed better than alpha. There's no rotation. What about beta? In the beta form, the distance between the 3-acylglycerol chains is shorter than beta prime and alpha. This is the best packing structure among these three. The better the packing, the higher the stability, meaning higher melting point. The better the packing, the higher the melting point. Okay. Beta has the best packing. Okay, let's see some examples of these polymorphic forms in foods. Here are some examples. So fats containing relatively few closely related tag molecules tend to form beta crystals, such as in soybean, peanut, corn, olive, coconut, cocoa butter, and lard. Highly randomized fats exhibit beta prime forms, and finer beta prime crystals are preferred in margarines and spreads, and larger beta crystals preferred in bakery shortening and in chocolate making. So the polymorphic form can be changed for a particular food application. Okay, let's answer these questions. What happens to some properties when we go from alpha to beta form? These three images are also very helpful to understand the polyformic forms. As you see, alpha is randomly packed, but beta is very well packed. It has the best packing among these three. So as we go from alpha to beta, density increases because beta is packed better. Alpha is the least stable form. Stability increases. It's more difficult to melt because it has a better packing. What about melting point? Again, it's increasing due to better packing. It will have a lower nucleation rate and slower cooling rates. So in order to have a good packing, you need to cool the 3-acylglycerol slowly so that they will have enough time to form a well-ordered structure, like in beta. Let's quickly review the factors affecting crystallization. 3-acylglycerol composition. Similar structured 3-acylglycerols form more stable polymorphic forms because they pack better, and randomized 3-acylglycerols cannot pack well, therefore they form unstable polymorphs. So presence of minor constituents such as monoacylglycerols, deacylglycerols, pigments may promote or inhibit depending on the size and the shape. They might promote crystallization or not, depending on the size and shape. And seeding means surface. Seeding provides surface area, therefore it promotes nucleation. It will help crystallization. cooling rate is an important parameter. Low cooling rate forms more stable polymorphs, but high cooling rate forms unstable polymorphs. Mixing is important. Mixing promotes nucleation because it increases the diffusion of the 3-acylglycerols to the crystallization site. So it's helpful. And scale of operation is important. When we say scale, even it can be the container size. Big or small containers affect heating and mixing rates, therefore affect crystallization. Okay, we will stop here. That's all for this lecture. Let me know if you have any questions.